In this video, I'm going to go over the valence shell electron pair repulsion theory. So this theory states that electron pairs repel each other, whether they are in a bond or not. So that is the main thing when you're talking about the Vsepr theory, which is the valence shell electron pair repulsion theory. What we are saying is electron pairs repel each other whether in a bond or not. Okay, whether in a bond or as a lone pair. So they are going to repel each other, and because of this repulsion, they always want to have maximum distance away from each other. Hence, this is going to help us be able to identify the structures which are going to be formed. Because electrons always repel each other, what is going to happen is that is going to help us determine the structure. So the first one, before we even understand about the structures due to the Vsepr model, we need to know something called electron domain. So what is the electron domain? So electron domain is a concerted group of electrons occupying the same general volume of space around an atom. So if you have got an atom, now electrons occupying the same space, general space around that atom is what we call the electron domain. For example, you can have a lone pair, you can have a single bond, you can have a double bond on this atom. So this one, there are 2 electrons, these are also 2 electrons, making 4 electrons, and then a double bond has got 4 electrons, making 8 electrons. So we can form a molecule like that. So here what is each of these, so this has occupied the same volume of space around the atom. So this would be referred to as one electron domain. This one has occupied the same volume of space around that atom, that will be considered one electron domain. Same, the double bond has occupied the same volume around this atom, it will be one electron domain. So for this atom, it has got 3 electron domains around it. So that is what is referred to as an electron domain. Alright. So whether a single bond will be counted as one electron domain, a double bond as also one electron domain, even a lone pair as one electron domain. So actually we can write an atom generally. If you have got an atom like this, take for example oxygen can form a double bond and a single bond and have a lone pair. Remember, a single bond has got 2 electrons, so 2 electrons, and then you've got 2 electrons there, and then a double bond, there are 4 electrons there, so making 8 electrons, and it means the octet has been balanced. So octet can form such a compound like that. Now we can generally write an atom in the form A, and then we are going to say X2 and then E. So this is representing if our oxygen is an atom, that would be if our oxygen is A. So this A is representing the atom, and then the X is representing these 2 other things on these 2 ends, and then E is representing the lone pair. So you've got E on top there. So we can generally write that in this form, just like it is here. A lone pair is on top there, that is our E. So a lone pair is supposed to have 2 electrons. Okay, and then we have got those bonds in the 2 directions like that. So generally we can write like that. Now let's understand how do we apply the concept of Vsepr, valence shell electron pair repulsion theory, to determining the structures. So if you have got, so the first thing we have what we call the domain geometry and also the molecular geometry. So if you are talking about the domain geometry, it's even including the electrons around that atom. That is domain geometry. Okay. But molecular geometry is not considering the electrons, only considering the atoms around that atom you are considering, or your atom of interest. For example, if you've got an atom X having a single bond, I mean a lone pair, bonded to X, and also bonded to X. So in this case, the domain geometry, are going to consider this one as 4 things around it, like that. So the domain geometry will be named according to how many things are around that, including the lone pair of electrons. But if you come on the molecular geometry, you are only considering only the atoms without considering the lone pair of electrons. So that is how we are going to go with this and be able to name structures with the domain geometry and also molecular geometry using the Vsepr model. So let's have a row where we've got, let's say we have got a row for domain geometry. We have got domain geometry here. And then let's find the shape. Let's have a part for a formula. What would be the formula? We can have another column for molecular geometry. And also an example at the end. An example we can apply on those. Okay. Let me make it in form of a table so that it looks much smarter and cleaner. Alright, so we are going to start. So we can have, if we have got a domain geometry that is linear, how is the shape going to be? So if we have got a linear domain geometry, so for something that is linear, we are going to have an atom here and then bonded to 2 other atoms like that. So this will be linear. Why? Because we only have 1 molecule here and 1 molecule there. Using the concept of Vsepr, atoms always wants to have maximum distance away from each other because these bonds contain electrons. So those electrons always wants to have maximum distance away from each other. Now if you have got 1 atom bonded to 2 other atoms, the only way that those 2 atoms, these can have maximum distance away from each other is when they make an angle of 180 degrees away from each other. That is the maximum they can be away from each other. So such a shape is called a linear shape. So the formula in this case is A x2. Do we have any electrons? So we don't have any electrons, so that will be E0. So the molecular geometry will also be linear. That is because we don't have any electrons in this case. An example that we can give is carbon dioxide, which is in this form. It has got 1 oxygen and 1 oxygen on the other end. It doesn't have, the carbon doesn't have any lone pair of electrons on it. So it has got a linear shape. Okay. We can also talk about a domain geometry which is trigonal planar. Trigonal planar. So trigonal planar, this is where you've got an atom like that and bonded to 3 other atoms in that way. So the bond angle they are making here, to have maximum distance away from each other, they are going to have a bond angle of 120 degrees apart from each other. So the formula for that one is AX3. There are no lone pairs of electrons, it's E0. So because there are no lone pairs of electrons, even the molecular geometry will be called trigonal planar. An example that we can give is boron bonded to 3 fluorine atoms in that way. So this shape is trigonal planar. So we are calling it a planar because it's a plane. It is just a plane. Alright. So another form we can look at is the domain geometry can be trigonal planar. But where one atom has been substituted by an electron. So what we can have is, we have got our A, that is still an atom, that is still an atom, but on top, instead of having an atom, we have got a lone pair of electrons. So therefore the formula is AX2 and then one lone pair of electrons. Now this shape will no longer be a trigonal planar for molecular shape. It is going to be a bent shape. So therefore the molecular geometry is going to be bent. Why are we calling it bent? Because it's going to be something like this. For example, if you talk about water, let me not use water because water doesn't have one lone pair of electrons. Let me talk of ozone. That is like that. So this one has got a lone pair of electrons like that. So when you're considering the domain geometry, you even count this electron which is there. So it will be trigonal planar because there are 3 things attached to it. But when you're talking about molecular geometry, you name it according to how many, just the atoms which have reacted to it. As you can see, only the atoms are meant a bent shape. It is bent. So that bent shape at times is referred to as the V shape. So that is the molecular geometry. Okay. The others, let me remove the table and then we start finding others. So remember what we are using is the Vsepr model, where electrons always want to have maximum distance away from each other. So if we go to a domain geometry which is tetrahedral, so we have got tetrahedral, okay, like that. So for something that is tetrahedral, it is going to be in the form, it is going to have the to take up the form A, where you've got an atom there, an atom there, an atom there, also an atom there. So that is tetrahedral. Okay. So this kind of shape, because all these which we can see, the electron domains, all of them are atoms. So the formula there is AX4. We don't have any lone pair of electrons. So even the molecular geometry is going to be tetrahedral because all these are atoms which have reacted. So the bond angle in this case, this is supposed to take up a bond angle of, is it 109.5 degrees to be away from each other. So the maximum distance is this one, away from each other. So this is a 3-dimensional object. It is not two-dimensional. Okay. So that's why it is a tetrahedral. I don't know how I can show it, but this is a 3-dimensional object where we are saying this can be towards us and then this one is away from us in the, like, somewhere towards the board, and these other atoms, one is above. So it is not like straight the way we can see on the board. No, this atom, it is pointing in our direction, this one is pointing in the other direction, this one is pointing in the other direction, and then this one is pointing up. That's why you can see it is tetrahedral shape. So they always want to have a maximum distance away from each other, so the angle, the bond angle is 109.5. Now the same domain geometry you can still have domain geometry. We can still have a domain geometry which is tetrahedral. But one of the atoms can be substituted with a lone pair of electrons, where we remove an atom. So we remain with 3 atoms, but we have 1 lone pair of electrons. So still this structure is something like this. We have got X there, we've got X, X, but here we've got a lone pair of electrons. So this shape, if you were to represent like using, let's say we want to use an atom. Let's talk of ammonia. Ammonia has got a lone pair, and then it has got H, H, and H like that. So the domain geometry, we are going to also consider the lone pairs of electrons. So the domain geometry is going to be tetrahedral. But for the molecular geometry, just take the atoms which have reacted. Okay? Remember the bond angle is supposed to be 109. So the bond angle between the atoms, and so if this was an atom, the bond angle is supposed to be 109.5, 109.5, 109.5, 109.5. But electrons have a greater repulsion than electrons in a bond. So there will be a much greater repulsion here. This will be pushed more down. Instead of the angle being 109.5, the angle will be reduced further. Okay. So the shape that you are going to have then for molecular geometry won't be a tetrahedral shape. It will be a trigonal pyramid. So the molecular geometry will be a trigonal pyramid. That is not a trigonal planar, it's a pyramid. So what's the difference? So this is forming something like a pyramid. We are saying trigonal because it's making like a triangle. If we consider down there, that will make like a triangle, and then these have bonded to the nitrogen on top there. So it is kind of like a pyramid, forming a pyramid of a triangle like that. So that is why the name comes in, trigonal pyramid. So the molecular geometry is trigonal pyramid. In that case, if you've got a lone pair of electrons and also 3 things bonding, the shape is trigonal pyramid. Okay, let's consider others. At the same time, we can have a domain geometry which is the same. So the domain geometry can be still the same, tetrahedral, but we have changed now. We have removed 2 atoms, they've remained lone pairs. So what we are having is A bonded to an X there, an X there, but this one we substituted it with a E, a lone pair of electrons, even on top a lone pair of electrons. Remember, if you have got 4 things around an atom, they are supposed to have 109.5 as the bond angle, but electron repulsion is much greater. So the way you can see these electrons, it's not like this one is on top, this one is down. No. So it is, we can take this as this one is coming towards this electron which is on top, is like coming towards us on top of the board, and then this one which is here is like coming towards us down the board, and then these 2 are going into the board on the down part. Even this one is going into the board on the down part. So this is not a linear shape. I mean, it's not a 2-dimensional shape. It is a 3-dimensional shape. So what we are going to form is, for example, in water, we have got an ocean where we've got hydrogen there, and then a lone pair of electrons, like that. So instead of having atoms there, we have lone pair of electrons. So the way we can see this is, this one is like coming towards us, even this one is coming towards us, and then these two are going into the board. So mostly we write that, we represent it as H. So where we put them like this, so that we don't think that this one is down, this one is on top, and then this hydrogen, since these electrons, this one is on top, this one is down, it's supposed to be straight because they want to have maximum distance away from each other. No. Alright. So therefore the geometry, the molecular geometry, is going to be bent. It's a bent shape. That is because these electrons have got a greater repulsion. So these will be pushed towards each other a bit. So electrons always wants to have maximum distance away from each other than atoms want to have, because the repulsion between atoms, between this one and this one, is not as great as the repulsion between these lone pairs of electrons. So electrons have got a greater repulsion. Alright, so that is the molecular geometry. Is a bent shape or a V shape. We can talk about another thing. Let's say, what can we talk about now? What of something that has got 5 things around it? If you've got something in the form AX5 without a lone pair of electrons, so this will be in the form A. Then you've got X there, you've got an X here, you've got an X here, an X there, and also an X there. So this is the shape which we have. So what is the name of this shape? So something in this form is called trigonal bipyramid. Trigonal bipyramid. Okay, I need to put an I here. I've forgotten the spelling for bipyramid. Alright, bipyramid. So why are we calling it trigonal bipyramid? That is because this down part is making like a triangle, that is trigonal. And then the bipyramid, we have got 2 pyramids. One is coming down like that. Then the other one is going on top in that way. So this is forming like a pyramid down and a pyramid on top. So hence the name trigonal bipyramid. So both the molecular geometry and the domain geometry has got a trigonal pyramid shape. Now the same one we can substitute, instead of having 5 atoms and no lone pair, we can remove like that, where we have 4 and then we substitute 1 lone pair. So we are going to have something in the form A. So in that form, so we can put one of them to be a lone pair of electrons. Let's say this becomes a lone pair of electrons, and then this is still our X, this is still our X, this is still our X, and this is still our X. So what we can see is the domain geometry is still trigonal bipyramid. But the molecular geometry is not trigonal bipyramid. That is because when you are naming the molecular geometry, you don't include the lone pair of electron like that. So this is what we are going to name. So we can rewrite this one in the form A, and then we have got X there, we've got X there, we've got X here, we can have X there. So this is the shape that we are going to have. So such a shape is called a seesaw. So this is the molecular geometry seesaw. Of course, there's a lone pair of electrons there. That's a seesaw molecular geometry. But for the domain geometry, it is still trigonal bipyramid because we even consider the lone pair of electrons when naming. Alright, what other can we talk about? What if two electrons have been have substituted in? So instead of having AX5, we have AX3 and then two lone pairs of electrons. So still even here, what we are going to have is something like, we have got A, and then let's say X there, X there, X there. So these two which are here, we substitute them with a lone pair of electrons each. So this is still the domain geometry is still trigonal bipyramid because we consider also the electrons. But the molecular geometry is not going to be trigonal bipyramid. Why? Because when we are naming, we don't include these here. Those will just be taken as a lone pair, like that. So therefore, the shape is called a T-shape. Because it even looks like a T, like that. So that is why it is called a T-shape. An example you can give is when you have got chlorine with fluorine atoms, like that, it's going to have two lone pairs in that case. So that will be a T-shape. Alright. What if we have something where we have got 6 things around the central atom? What shape is it going to take? So if we have got A and then X6, we don't have any lone pair of electrons. So the central atom is here. We have got X there, we have got X there. Then we've got X there, X there, X there, and X there. So this is an octahedral. So this is called an octahedral. So we can make it look like this. So the same way I've written it, we can also write it in this way, where this X is here, this X is here, and then we have got like that. It is the same shape. It is still an octahedral. So we can write it like that. Then this one is going on top. This one is going on top, like that, finding the electrons which are on top. And then these down ones are also coming like that. So we can see that this is also a rectangular pyramid. Okay, so the octahedral is a rectangular pyramid. Alright, so that is what we have, octahedral, both for the domain geometry and also the molecular geometry. That's octahedral. Octahedral. Alright. So we can have another one where instead of having all 6 electrons, 6 atoms, we are going to substitute one with a lone pair of electrons. What shape is it going to become? So I have AX5 and then a lone pair of electrons. Okay, we have one pair of electron in that way. So it is still in the form A. So this is still X, this is still X. We have X there, we have got X there, we have got X, but this one we've substituted with a lone pair of electrons in that form. Okay, so that is what we have. So the domain geometry for this one is still octahedral. For the domain geometry, octahedral. That's domain geometry. But for the molecular geometry, we are removing this portion. So what are we remaining with? So what we are remaining with is forming something in this way. Okay, this is something that has been formed. So this is named as a square pyramid. So we consider this as having the same angle. So even the previous one which I showed, the octahedral, which was in this form, let me just show that again. Instead of saying rectangular, let's see what is happening. So this thing which I showed earlier, it was in this form. So it is not supposed to make a square like that. It is supposed to make, it is not supposed to make a rectangle. It's supposed to be a square, something like a square. Okay. So we have this. This is what we said is octahedral. So it is also a square by pyramid, because we can see two pyramids by pyramid, which is also called a octahedral. But if we remove one portion of atoms and then we substitute with a lone pair, it turns into something like in this form. And then we have got another atom here. So this one has become a lone pair. But for the domain geometry, we don't, the domain geometry is still octahedral, which we can also say it is a square by pyramid. But for the molecular geometry, what we are forming is, this is supposed to be a square. I want to make it a square because the angles are all the same. Of course, it's looking like a rectangle, but it's supposed to be a square. Come in. It's supposed to be a square. So this is what is being formed. So such a thing, as we can see, is a pyramid going down. So this is a square pyramid. So that is the molecular geometry for this one. Square pyramid. And then we can have another one where instead of having 5 electrons, we have 4. And then you have got 2 lone pairs. Then what will be the geometry? The domain geometry is still octahedral. But what are the molecular geometry? So what we are going to have is we are going to have something in the form, we have X, we have got, okay, we have got like that. This is our X, this is our X, X there and X here. But these two have been substituted by electrons. So what is this thing now? So those two electrons, counting them, that will give us octahedral for a domain geometry. But for molecular geometry, when we are reading, we don't count these lone pairs. So those lone pairs will remain there. So this kind of shape which we have is going to form what we call a square planar. A square planar. So it is a plane. Yeah, it is a plane. That is why we call it a planar. It is not like a pyramid, it's just a plane. So that is how we can tell the molecular geometries and domain geometries using the valence electron pair repulsion theory. Thank you so much for having been together in the video. Stay blessed.